I feel the master. I feel them. Y'all ready? They ready? Well, come on. Well, come on. Y'all ready? They ready? We ready?
The materials that we used for our project was this Husky tarp. Shout out to Husky for sponsoring this video. We chose this tarp because we needed a surface that was slick enough to reduce friction when we were going down the slip and slide. We used soap as a lubricant for the slip and slide, so when we went down the slip and slide, it would reduce the friction. We used the cooler here for water, and we filled it up with water, and as we were doing our runs, we had water going down the slip and slide just to keep the surface constantly wet. To set up our experiment, we first filled our cooler with water, so we had a constant stream of water coming down on the tarp. We then laid out our tarp and placed 4 very heavy rocks on each of the corners. This was to keep the tarp from moving when we were moving around on it. We then conducted 3 trials, and we layered fresh soap before each of the 3 trials. To conduct our 3 trials, we first lubricated the slip and slide with the soap we bought. We then started my brother from a position of rest and dropped him down. We calculated the time that it took him to reach the bottom.
Ready, set, go. Two, 1, go. 2, 1, go.
So eventually what we need to find is the force of friction of the object going down the slide and the slide itself. So the first thing we need to do is solve for this x using the Pythagorean theorem. X squared plus b squared equals c squared. And for x, we get, when you do the calculations, we get 24.5 feet. So now we can plug that in for x equals 24.5 feet. So now we have that. So because we did that, so then we can eventually solve for theta here. So to solve for theta, we're going to use the law of sines. So the sine of this 90-degree angle here over 25 feet right here equals the sine of theta here over 5 feet. Eventually, when we solve this all the way through, we'll eventually get to 0.2 equals sine theta and then just do the inverse sign, multiply by the inverse sign both sides. And this will get us a value for theta of 11.5 degrees. So now this theta right here, we know is 11.5 degrees. This is important because now we know the slope of our hill. So now we're going to make a free body diagram to help us find the normal force, and we'll go from there. So free body diagram, going down the slide this way, acceleration. The force of friction is going the opposite way. Shorter line than longer. Force of gravity is going straight down. And then normal force is going up off the slope. And then we have another force called this force is the component of gravity. So it's coming straight down from the normal force. So it's going to make a dotted line right here to represent that. And right here we have a angle theta. Now this angle theta here is equal to the same angle of theta here, which we have already solved as 11.5 degrees. So to find force normal, we can use the force of gravity, which is mg, times the cosine of this angle theta here. Now again, this angle theta here equals this angle theta here. So when we solve that, m, our mass of our object, or name Jack Bevington, he was 36.3 kilograms times 9.81 meters per second squared times cosine of 11.5 degrees. We can solve that to get a normal force of 348.95 newtons. So now we have a normal force, which is used to find the force of friction. So now that we have the normal force to find the force of friction, we now want to find the coefficient of friction. How we do this is we look at the free body diagram to first understand net force. Net force is going to be the component of gravity minus the force of friction. That's how we're going to get net force. Component of gravity minus force of friction. Now we also know that net force at the beginning, since we're starting from 0, is going to be 0. We can then conclude that the force of friction is equal to the component of gravity, because if you solve this equation right here, you can just add force of friction to the other side to get force of friction equals force component of gravity. Now, these force of friction right here can also be represented as coefficient of friction times the force of gravity times the cosine of theta. We know that by looking at our free body diagram. And that equals the component of gravity. While looking at the free body diagram, we can also conclude that that also can equal force of gravity times the sine of theta. Now with this equation right here, we can, because the force of gravity is on both sides, we can cancel those out to get coefficient of friction times cosine theta equals sine theta. Divide both sides by cosine theta. Coefficient of friction equals sine of theta over cosine of theta. Sine over cosine equals tangent. Coefficient of friction equals tangent theta. Now, theta again is 11.5. Tangent 11.5 degrees is going to equal 0.2. So now we have both the coefficient of friction and the normal force. So now we have used the law of sines to solve for theta. That theta was then 11.5. We used that to solve in this equation to find the normal force, and then we concluded that the force of friction is going to equal the force of the component of gravity. Using those equations from our free body diagram, we were able to solve for the friction coefficient. Right? Is that coefficient? All right, friction coefficient.
No.
So then with those, multiply those together to find the force of friction. To get a value of 69.79 newtons. We now know that the force of friction between Jack Bevington and the slide is 69.79 newtons.